So you're given two problems, the first of which asks you to find the greatest common factor of a pair of expressions, 15a to the fourth and 12a to the third. And the second problem, which asks you to factor the expression 15a to the fourth minus 12a to the third. So let me start by asking this question. How are these two problems related? Okay, so they both have the same numbers, the 15s and the 12s. They also have the same variable factors, the a to the fourth and a to the third. So both of them are asking about the same pieces, 15a to the fourth and 12a to the third. So what's the difference between these two problems?
Second one makes you do another step.
Second one, you have an extra step to do, right. So probably, if you did both of these problems, you probably did the problem on the left first, and then used your answer to the problem on the left to do the problem on the right. And just to fit this problem into our grand scheme of thinking in our content on factoring in this course, the greatest common factor method, the one that we're talking about today, for any factoring problem at all, should always be your first step. So even later on, when we start moving toward more and more complicated expressions and more complicated ways of factoring, your general factoring strategy should always begin with what we're talking about today. So definitely hang on to these notes, because this is a way to take even a more complicated problem and start to make it a little bit simpler, to begin that process of breaking apart a polynomial expression to discover what its factors are. Okay, so from left to right then, how did you find the greatest common factor of 15a to the fourth and 12a to the third? So all right, so you said you started with the numerical coefficient, started with the 15 and the 12. And you said that when you thought about the greatest common factor of those two numbers, you got 3. Now, why is that?
Because 3 can go into 15 5 times and 12 4 times.
Okay, so sometimes we'll depict that by drawing a little factor tree like this. 15 is 3 times 5. 12 is 3 times 4. And so we know that 3 is a common factor for both 15 and 12. Why is it the greatest common factor? How come there's not another number which is bigger, which is also a factor of 15 and 12? So 3 is the greatest common factor because the leftovers over here, 5 and 4, those leftovers, 5 goes into 15 and 4 goes into 12. Well, what's 4 made of? 4 is really made of a 2 and a 2. Right? We can't break that 4 down any further. Right? We similarly can't break down the number 5 any further. Because what kind of numbers are 2 and 5? What do we call them if we can't break them apart any further? Yeah, they're prime numbers. So we've broken these numbers down all the way into their prime factorizations. And we can look and see that 2 doesn't go into 15. So we know that we can't do any better as far as fitting any of the factors of 12 that we haven't accounted for into 15. And conversely, we can't fit the remaining prime factors of 15 into 12 either. 5 doesn't go into 12, 2 doesn't go into 15, and so we're done. Another way that we might say that is that the cofactors that we broke out here, the 5 and the 4, they themselves have no factors in common. Right? So there's nothing else that we can latch onto if we were to try to factor it any further. So 3 is the greatest common factor of 15 and 12. So what did you do with that information? What comes next? Now that we've figured out what the GCF of those two coefficients are, what else did you do? We need to find what the greatest common factor of a to the power 4 and a to the power 3 is. And so you're looking at the two of them and said, well, one of these actually goes into the other. Right? Which one? A to the third actually goes into a to the fourth. If we wanted to, we could break that out with a factor tree as well. A to the fourth is a to the third times what? A. Times a. After all, if we were to multiply, and this is the other thing you were saying, if we were to multiply and try to go backwards, a to the third times a to the first, what do we do to exponents when you multiply powers? Add the exponents. And so we would get back to a to the 3 plus 1, or a to the 4. Right. So if we were to try to break this out in sort of a prime factorization tree like we did above, right, both a to the fourth and a to the third have this common factor of a to the third that lives inside of them. Right? And the leftovers that remain after we factor a to the third out of both, don't have anything in common, not anything interesting anyway, between a and 1. There's nothing that's common to both of those. So a to the third is the greatest common factor of a to the third and a to the fourth. Does anyone know what a shortcut might be? We compared two powers of a, and we chose one of those two answers to be our greatest common factor. Which one are we always going to choose?
Low one.
Right. We're going to choose the one with the lowest exponent on the respective variables. Let's say on the respective bases, because this also works when those bases are prime numbers. So right, in a choice between two powers of a common base, the greatest common factor is going to be whichever exponent is smaller in either of those cases. So we know now the greatest common factor between the numbers, 15 and 12, is 3. The greatest common factor between the two variable expressions is a to the third power. So how do we put those answers together into the greatest common factor of these two monomials? What's our final answer?
3a to the third, parentheses a, 5a, sorry, minus 4.
Okay, so the greatest common factor is 3a to the third. So the answer to the question on the left is just that GCF, just that expression. But then what you also told me is that we can use this answer to take it one step further and do the problem on the right, which asks us not what is the greatest common factor, but how do we use that information to factor as a verb, right? This expression, 15a to the fourth minus 12a to the third. So let's talk about that piece to finish this up. So now that we know that 3a to the third is not only a common factor, but is in fact the greatest common factor between these expressions, here's the frame I want to put on this, because we used this frame when we were talking about multiplying polynomials last week. We can use the same frame when we talk about factoring. When we multiplied polynomials, we used this little grid to say, let's put the terms of one of the factors around the first row and the terms of the other factor down the first column, and we can use this grid to organize all the multiplications, all the products that go into our finished answer when we multiply two polynomials together. Well, factoring is nothing more than the opposite of that process. So when I multiply polynomials, I work from the outside of this grid in. But when I factor polynomials, I'm going to work from the inside of this grid out. Factoring is nothing more than the reversal of the process of multiplying polynomials. So what I'll do is I'll take the expression I'm factoring, 15a to the fourth minus 12a to the third, and I'll put that on the inside of my grid this time, one term per square in my grid. Then all I have to do is work my way outside. And to get that process started, I need a place to plant my feet. I need a first sort of opening move to get the ball rolling. And the greatest common factor does that for us. Because what it's going to do, if I write the greatest common factor, 3a to the third, out here, is it's now set up for us a process by which we discover what its cofactor must be. And this is where the sort of thinking backwards portion comes in, where we ask ourselves, and I'm going to go back to you, Samantha, how did you find out what went inside those parentheses for your factorization of this in this step of the game?
Well, if you divide the 3 by the 2 coefficients,
Okay.
you get most of it.
Right, so the first thing you do, again, because this is the opposite of multiplying, we can think about dividing as a way to get there. So if I divide the 3 out of both of my coefficients, out of the 15 and the 12, as you say, that gets us a good step of the way there. 15 divided by 3 is going to give me a 5. Minus 12 divided by 3 is going to give me minus 4. Okay? So we can check now that we've got the numerical coefficients right. If I were to multiply, again, this was your other point, if I re-multiply, go from the outside in, I should arrive at the right numerical coefficients. 3 times 5, 15. 3 times minus 4, minus 12. So far, so good. Now what am I missing in my cofactor?
You're missing the a in the first term.
Right, so on my first term here, I need an a. And how do I know I need an a right here?
You multiply the a to the third by the a, you get the a to the fourth.
Yeah, I need it to be such that when I multiply my powers of a, my a and my a to the third, I need to get a to the fourth. Right? And so you're asking when you're working from the inside out, what do I lack? If I didn't have that a sitting there, then in order to multiply 3a to the third by this thing and get 15a to the fourth, what I'm missing is I'm missing 1 power of a. So I'm comparing, I have 3 on the outside, 4 on the inside, so I'm missing 1. So that's the artistry, that's the creative process of factoring, is that backwards thinking, that almost design thinking in a way. What am I missing in this factor that I need to have in order that when I remultiply, I get the thing that I need to get? And right, so that's the last thing to do, is now to put this sort of grid back into the form of an algebraic expression, which we'll do by remembering to include any polynomial inside a set of parentheses. So my 5a minus 4 becomes an expression enclosed with parentheses, 5a minus 4, and then its cofactor was my GCF, 3a cubed. And then that becomes my final answer. So once you know the greatest common factor of 2 monomials, you can use that greatest common factor and what we say is factor it out of an expression which is made of those monomial terms. So we factored 3a to the third out of both of these terms. And the yellow portion, what was left over, are the extra pieces that help to complete that original picture. It's what's left over after the 3a to the third is factored out of each of these two terms, respectively 5a from the first term and minus 4 from the second term.